Again, thank you for your attention. Thank you, Brian, for allowing me to come and share a little bit about some of my work. And today I'm going to talk a bit about web maps and big data. And raise your hand if you've heard of Buckminster Fuller, if you know who that is. Awesome. We're going to talk about buckyballs today. So hopefully it's interesting. It's a bit different than that last one we just saw. So we're going to take a right turn. A little bit about me. My name is Will. I'm a web developer. I have a specialization in geospatial. So if it has to do with maps or GIS or data visualizations, that's where my sweet spot is. This map is my last map that I was working on this week. I work for a nonprofit in Oregon, and we're working on the Rogue River Basin. So this is the river basin, and we'll get a little bit more into this map just a little bit later. But that's a little bit about me. I love maps. There's going to be a lot of colors in this presentation and a lot of maps. So if that hurts your eyes, then make sure to put your sunglasses on. I love data visualizations too. So that's my thing. Here's my stack, and this is an open source meetup. So just want to throw that up there and point out a few things. I like to be here. I like to do the maps, and I like the visualizations. Also, my favorite backend, PostGIS is our backend, and I'm going to point that one out because this is the geospatial component that is an add-on to PostGIS, which allows basically GIS operations in our backend. So this is a super powerful tool, and I love it. So we're going to talk about the problem. What is the problem? The problem is big data and a lot of points that can go on a map. What we're looking at here is a 15,000 fictional, I'll put that in quotes, fictional restaurant, fast food restaurant in the United States. If you take a look at this logo down here, you might know what we're talking about, but I'm going to refer to them as McDowell's in this presentation just to make it a little bit anonymous. So the idea is, what can we get from, if you look at this map, what kind of things can you see? How can you get the idea of where the density of the stores are? I mean, obviously in the eastern side of the country, there's more of these McDowell's, but where? Is it New York? Is it Chicago? Is it LA? There's no idea with this kind of a map. So we're going to look at some ideas of how we can get ourselves into this kind of data, because it's increasingly, as our cell phone collects hundreds of points of data almost every minute, there's billions of rows that are being written by this device. So it's something that if we're trying to make sense of what's going on underneath us all, we have to find ways of getting through all this clutter and all this big data. First, I want to talk about one method to do it, and that's called a heat map. You've probably seen a heat map. Basically, the idea of a heat map is it's where it's red, there's more. And in this example, we're still looking at the same data, the McDonald's restaurants, zoom in on Chicago, and then finally we get to a point where we can actually see point data. So there's one method of doing it. It's a little bit, we see a little bit more here, a little bit more information comes clear here in this version than we saw here. You can see where it's some of the spaces here are showing up, but it's still sort of a blob. So we're gonna keep looking. Another way that you might have seen, this is a cluster map, and this is Google has these. And what it's doing is, if you pay attention to the points here, the points here are, the pins are the actual locations, and then these other things are groupings of the McDowell's, where yellow is a little bit more, and if you look at the number, you can see how much is going to go under there. The problem with this kind of a map is it's this little cognitive little jump that you have to make in your mind to go like, look for the color, look for the number, that kind of thing. These maps are pretty simple and people can understand them, and it's a good way of doing that. The other problem with this sort of a map is it doesn't do well with a national scale. You can see here that I'm zoomed into Denver, and we're looking at that area. If I threw the 15,000 points at this Google map, it would not be able to be very performant. So hex bins. What are hex bins? How could these things help us? The idea, hex bins are everywhere. You probably see them. There's like in the zeitgeist right now. And the idea that what we're going to do is we're going to put this layer of hexbin over the top of our map. And then like a regular choropleth map, we're going to darken where the areas are. And we're going to either have bigger hexbins at a larger scale, and as we zoom in the scale, the hexbins are going to get smaller. And that's going to be like a lens over our map to help us make some sense of the density. This is a map that I made maybe a year and a half ago. And this is not McDowell's locations. This is actually Starbucks locations. And what you can see here, what we're looking at is, I can't remember where Starbucks first came into existence, 1993 it looks like. But you can see how basically how the growth of Starbucks has happened since this goes up to 2017. And it does more, this map does more than just show that. If we, I'm just gonna play a little bit of what you can do with it. And, oops, sorry. So same sort of thing, we're showing the density, but then I'm gonna zoom in here to Southern California and hit this redraw grid. Now, if you watch what happens, the grid changes, the hexagons are getting smaller, and we're able to like really get into the density. In this map, I didn't go all the way down to the level where you can get to the location, but you can get the kind of, you can get this, you see the idea of what we're doing here. We're going to be able to go all across the country and get a chance to zoom into the density. Here I go over to Chicago. I'm going to check out how many Starbucks are in the loop.
We have the largest Starbucks in the world now.
Yeah.
I was there a week ago.
I was there over Thanksgiving. It was amazing. Yeah, it used to be it's on Michigan Avenue, like the main strip in Chicago. If you like Starbucks, that's the one to go to. So a little clunky that you got to press those buttons when you press the button to redraw the grid. We're going to see a better iteration of this hexbin idea coming up. So just to compare the two ideas, we have over here, this is a good illustration of the differences. Both of these methods are to show density. This here is back to the heat map. What this map is showing is this person was doing a bicycle ride, and where it's blue, that's where he was stopped. He actually took time to rest. So you can see here where these are the places where he was stopped, but you can't really tell where did he stop the longest. If I use the same data and use a hexbin over there, it's clear that he was spending his time here and here and here. So I don't want to really say many bad things about heat maps. I love them too, but if you're going to go for a little bit more of a, that's cool, thank you. If you're going to go for a little bit more distinction, we're going with hex, and that's what we're talking about in this presentation. The other cool thing that you can do with hexagons is you can extrude them. You can make them 3D, and this is example. Imagine that we have poker chips on top of our geo layer that we're going to try to tell things about, and these could be different attributes according to that are attached to what's going on underneath in this spot. So if we three-dimensionalize it, we can stack different attributes, and that would be another thing that couldn't be done with a heat map, which is more of a raster type of thing. Here's another example. This was the same map that we looked at earlier, but what this is I'm just trying to illustrate the idea of the stacking. This is a river basin, and each portion of the river is divided into segments, and each bar here is attached to one of those segments. So if we zoom in on one, we're kind of seeing that what this is really showing us is what they call uplift. So they're doing best management practices around this river, and this is the predicted uplift. And I don't remember what orange means, but it is one of the attributes that is going to be the contributor to one of those uplifts. So it's kind of the idea that we have this extrusion, and we can do that more easily with web maps today. Also, just to put the final point on extrusion, this is the Starbucks data that we saw earlier. And if you remember back here, we were looking, when we saw it, you know, you can see that Manhattan here is pretty dense, and Chicago is pretty dense. but they kind of look the same, you know, looking at it this way. If I get it back to here, this is the exact same data. Manhattan, sorry, Chicago, I know you have the biggest Starbucks, but Manhattan, you have the most, at least it was in 2017. So that 3D dimension can really point out the differences very, very strikingly. So basically what we're looking at is that there's our problem and there's our solution. And I'm going to do one more comparison between the two types. There's heat map and there's a hexagon map, and that's what we're aiming at towards the end. I would argue that you can see more in the hex map. Like you can see that it's Southern California. You can see that it's New York here. It's in here. It's still stuck in the wash. So we're going to go with hex maps. And the cool thing is that we can use an open source library to get our hexagons. And Uber wrote or created this Hexagonal Hierarchical Spatial Index. What I want you to take a look at is it's basically like we got the globe here, right? And you can see the bigger hexagons are on the outer shell of the globe. Inside we have like 6 hexagons underneath. And this index, the system, has 16 levels of this. It goes all the way down to the meter level. So the smallest hexagons are this big. And there are millions of hexagons. I don't know if there might be billions. I never got the exact number. I know that at level 6 for the continental United States, there are 10,000 of them. So that will give you a sense of what numbers we're looking at. Here's another view. This is California. You can see over on the left that we're looking at a higher view mixed with the lower view. And here is, I don't know what level that is. You know, that might be 6 or 7. Goes all the way down to 15. And so what you want to think about is it's like an onion. Every wrapper of the onion, it gets the resolution gets a little bit small. It gets smaller, right? So that's one way to think about it. And also think about it as a soccer ball. Soccer ball is made of hexagons with intermediate pentagons, and it's the same sort of idea. So why did Uber need such a thing? And here's this slide will help. They had a problem when they first started. It was called phantom demand. And what we're seeing here over on the left is this is an Uber driver. And this one thing to note is this map here isn't hexagon. They didn't have hexagons yet. This is San Francisco, and this is the Uber driver. And so as you probably know with Uber, the drivers get a notice and it says, go to this location. You're going to be able to pick up some passengers. So this poor Uber driver is over. He or she's almost in there in the right spot. Gets the call and says, go to this neighborhood. That's the dark red one. She goes into the neighborhood, but is in the wrong spot because the concert is letting out up here, and there's not a connection. And that was the problem. They were using this old kind of neighborhood administrative boundary for their mapping, and there was a lot of this breakdown. So it was poor for the riders, poor for the drivers. It would be like, they told me to go here, wasn't happening. So the point, this comes from this project, and the main idea to take from it is that there is a clear center of demand, and maps that can be created from this have a smooth gradient. Also the idea that we're going to do away with administrative boundaries. We're not going to worry about counties or neighborhoods or states. The boundaries that we're going to be paying attention to are dynamically created through what's being asked for within within each hex bin. If this interests you, there's a great presentation. This is the engineer at Uber who put together this idea. It's a really great, and part of my presentation borrows a lot from this. So if you're interested in hex bins, that's a great one to take a look at. So did they just start drawing hex bins? How did they come up with this idea? Well, the cool thing was they looked back, and this is where Buckminster Fuller comes into play. Buckminster Fuller is basically he's a genius. He wrote, you know, he's an inventor. He was the president of Mensa. If you've been to Epcot Center in Florida, you've been in Buckminster Fuller's world. He invented this kind of an idea. Here he is. I think there's a monorail over there. I think this is probably when Epcot was being built. So he did a lot of things, and buckyballs, as you mentioned, that's one of my favorite toys. If you want to build a geodesic dome, there you go. These are little magnets that you can hook together in crazy ways. And why are we talking about Buckminster Fuller? Well, he made a map projection, and raise your hand if you know what a map projection is. Does anyone know? Okay. Well, a map projection is a way, the best map that you can ever really, the best, more correct map that you can look at is actually a round globe. And the idea of a projection is there's a way that you have to mathematically kind of warp the globe into a flat. And we need, in order to have a flat, what we're looking for is for a screen or paper. And there are many different ways of doing it. Here's some examples. You can see how there's many different ways of looking at that globe, and there's many different ways of getting a flat map out of it. The one thing to remember is that all of the maps produce distortion. And when I say distortion, when it has to warp that round into this flat, it is going to change the shape of the geometry, or it's going to change the size of the geometry. And this illustrates that really well, because these are all different projections, and each one of these projections does this to South America when it produces it for the flat version. The reason why I'm talking about distortion, well, I'll talk one more. You might have remembered this from 3rd grade. This is the map that you had in your 3rd grade class. And you might remember that Greenland looked huge. Well, Greenland really isn't as big as South America. Greenland is only 1/15 the size of South America, but it's because this projection is really focused on keeping the accuracy around the equator. It's not concerned with keeping the accuracy of the size at the poles. So this one exhibits distortion at the tops and the bottoms, and that's why Greenland is so stretched out. That's a great example of what distortion can do. Hoover doesn't want distortion in their scheme. That's why they picked up on Buckminster Fuller's Dymaxion Projection. And I'm not going to read that, and I don't know, that's some kind of a hedron. But the point is that I'm going to show you a picture of what it is. The point is that Buckminster Fuller's projection is very good at limiting shape and distortion, or any distortion in shape and size. And this is a great little animation that you can see. I'm going to throw these out too. So you can see right there, as we're at the flat, if you look at the continents, they are really well, they're very much in proportion with each other. And but this is not a map that you might not want to put on your wall, because it's, the continents are all upside down and things. But the point of this projection is that it limits distortion. And I'm going to pass these around. These things can be folded. Take a look. So that is the folded up Dymaxion projection. The thing to note, there it is right there. The thing to note that when you look at that ball, that paper ball that we have, the corners, these corners here are all the pointed corners on the map. And also, look at where the corners are. Look at how he created it so that the points of most distortion, these points, those points on the globe, are not over land. So he put even when he made this projection and the limited distortion, he also put the points where there were distortion out in the ocean, where it made less of a problem. So it's cool in my mind. There's just pointing them out. One of my favorite web comics is XKCD, and they did a kind of a joke post about the Dymaxion projection. And basically, if your favorite map projection is Dymaxion, then you like Isaac Asimov, XML, shoes with toes, and you think that Segway got a bad rap. You own 3D goggles and you use rotating models of better 3D goggles. You type in Dvorak. I don't type in Dvorak, but I do like the Dymaxion projection, and especially because it's become useful in this way. So what happens when we put the hex bins on our globe? You can see here we have all the hex bins, but weirdly, or maybe not weirdly, is that some of them are pentagons. Kind of like how the soccer ball is, mostly hexagons, but some of them are pentagons. And the interesting thing about it is where those points are, where those pentagons come into play, those are the actual points on the map that is on that globe. So it was a cool like echoing of the Dymaxion projection in the in Uber's H3. So when I was exploring this, I'm like, I was finding them like, there's a pentagon, and then I started unraveling why there's some of them that are only 5 instead of 6. Those are those 3 over here, and
Are those all actually aquatic? Or are they-
yeah, all the points are over ocean, and I'm gonna.
One was on the land, top wasn't it?
Really? I don't think so. They might be right next to land. So here I just showing you, there's my globe. As you rotate it, you'll see the hex pans come back, and then
That top one there, is that over land or water?
I don't think they're any over land. I think they're like right on the edge of land. So anyway. So how are we going to get, how do we get, remember we're talking about McDowell's restaurant data. And so what we need to really do is get a count of how many restaurants are in each one of the squares. And we have to go all the way down. And what we're doing here is using open source tools to do so. This is QGIS, and this is the open source GIS program where it's going to do counts, and that's just me showing me that I started pulling these hex bins into my program. And here's Denver. You can see just another, you get a more sense of how the sizes are. Here I'm zooming into Coors Field so you can get this sense. I didn't go all the way down to the billions level on the 15th level. I think in this project, I only went down to the 6th level. Here's a glimpse of the SQL, and I'm pointing this out because it just brings about another open source tool called PostGIS that I mentioned earlier. And I can do some GIS processing here, basically in a SQL statement. So that's the reason I really like it. Oops. So here's our map. Here's our final version, or not final version, but this is our iterative version that we are at right now. And you can see here that I'm zooming, as I zoom in, unlike the Starbucks map that we had earlier, the hex bins are updating. The hex bins are getting smaller, and the density is becoming more clear. So as we zoom in on Los Angeles, we're going to finally get down to the point where we just keep going towards the dark one, and we're going to see where the most dense area of it is. And when we hover over one, we can get there. I think in this video, I go over to Chicago like I did with the other one. As we zoom out, we're zooming back out through the hex bin layers. They're going to get bigger, and then we're going to zoom into Chicago, and they're going to get smaller, and we're going to be able to get an idea of the density.
Could you differentiate floors in a building?
Yeah, yeah,
Because that's often a need, right, for carriers.
yeah. I mean, the 3D possibilities that are possible with Mapbox are pretty amazing. So definitely. So this slide is basically showing that you can see that what happens in that last version as I'm updating, there's a little delay as it hits the server because it has to go and say, what are my hex bins for my current extent of the map? And it's a little bit clunky and a little bit slower. If I was to go further into this idea, there's the idea in a web map that you have a base map. And if you look at any sort of map, like a Google map, you know, there's a lot of data on the map, but it doesn't have to load all that data. It's really fast, like the roads and all the details are already there because those are baked into the base map. And what I've done here is I've taken 3 layers of hex bins and put them into the base map, and it's much smoother. There isn't a hit on the server every time that we move. So that's the direction I would go. Of course, we don't have the data joined to this, and we're not seeing McDowell's data, but I think that because we would not be sending the geo information over the pipeline and just the data and saying, okay, that hex bin has this count, and then it's going to be symbolized in that way, it would be better. So that's where I would go if I was going to continue with this idea.
So it looks from here that the Hexagon, they're
No, they actually kind of go outside of the, yeah, they're not this, they're not exclusive to their parent. That's true. I don't know what happened there.
So Uber actually superimposed them on the globe. Those are all fixed in space.
Yes. Yes, they are. So a little bit about, let's talk about use cases of this type of map. And I struggled to think of some more use cases. I can tell you what we were using it for, which was to, we were using the hex bins because the company that I worked for was trying to find usage of their network. It was a cable company. So they were just, inside those hex bins they were calculating how much data is being sent over the pipeline. And then they would use that information to basically improve their network and replace it. But here's some of the ideas, and maybe these can spark ideas in you. And that's part of the reason why I'm here, is get some ideas out. If you have a ton of points and you want to see underlying patterns, hex bins are something that you might want to consider. And if you can think about times when it doesn't make sense, like in the Uber example, that we don't want to rely on administrative boundaries, we don't want to think about maps in terms of neighborhoods or counties or states. We want to make our maps that are connected to what is actually happening. And hex bins are dynamic and they work at any scale. Also, like I talked with the stacked thing earlier, is that the hex bin can deal with multiple attributes. And so that's where they can come into play and be a little bit better than heat maps. I thought of some other things that might come into play. I think that emergency response, it seems like more emergencies seem to be coming and going these days. And the thing that you need to know, the thing that's important about emergencies is that you don't know where they'll happen, but we know to be in the exact location. And that kind of like is echoing what the Uber thing was. They need to know, you need to get to that, you need to make the connection from the need to the deliver as quickly as possible. So that might be one that could spark some ideas. Yeah, yeah. I mean, I would love to hear ideas like that, and I would love to apply this idea on that. Another idea that was in my world more last year is the Internet of Things, and that, our phones are the things that are keeping track of all this geodata primarily, but increasingly everything has the ability to have this point data. And also kind of a good that goes along with that is the shared economy. Like today we can share our house with Airbnb. We can share our car and be our own car rental. These scooters are everywhere. I feel like it's gonna be more of these things where people are trying to provide services just to other people. And these kind of things lends itself to these kinds of maps. And also it might help you to understand like where you could see an opportunity. Like if this hex bin has this much activity, and you can align it with, say, an income level within that hex bin, that might tell you that another hex bin in the earth, basically a GIS question of like, what's a similar hex bin with these attributes? Let's go put our opportunity or our product in that area. So I think the sharing economy has a really big part of it. And this one on the left, this slide came from this company called Helium, and they are an IoT network, and they have connected cryptocurrency to their IoT network. So basically it's a network of machines. Whatever happens in the machine, they can pay each other in micropayments. And this is a map. You can see they're clued into hex binning, but it's a little bit like the cluster mapping in the beginning. I think once their network grows a bit, they're going to do more closer to what I showed earlier with these hex bins. Here's another idea: social media. This is Tweep's map. I typed in the hashtag open source, got a nice map, but unfortunately it's like in the context of this presentation, we're using administrative boundaries. It's cool that America is a leader in open source tags on Twitter, but maybe it would be cooler if we could see an hexbin map version of that. They do have a city version, but still, you still got to make that translation in your mind. That's a little bit better. Wouldn't it be better to see something more like that? I think maybe it would. Also, that's my other thing. If you have other ideas like what you just mentioned with the DDoS would be any kind of ideas that this kind of idea could lend to. If you have such ideas, I would love to hear about them. And so there's me. I'm on LinkedIn, and if you're interested, I would love to talk to you about what these things are about. Thank you.
Any questions?
Yep.
Make a quick observation that we've done GIS before.
Yeah.
I saw, like, you talked about administrative boundaries,
Right.
like in computer science, we can derive like arbitrary boundaries from whatever we want, including like in the network, we get arbitrary boundaries, whatever we want to have. They didn't have that in GIS. And when they built these arbitrary 16 layers of different boundaries,
Yeah.
that like that totally unlocks, gives you like a framework to hang everything else off of.
Yeah.
Building your own
Yeah.
over and over again. Like we did 911. It's inextricably tied to the geographic boundaries because the call centers are literally tied to like counties and cities and stuff.
Yeah.
We draw these maps, but yeah, that's just outstanding. Like that's amazing.
Yeah. Yeah, the one slide, the guy from Uber that basically was the engineer from behind it, they go through like all the different types of binning things. They do like squares and triangles. So it's totally cool. Anyway, thank you.
Thanks, Will.
Yeah.